Okay. All right, well, we're going to work on some more examples. We're going to look at the closed interval method from 0 to 2 pi for this function. F of x is x plus sine x. There's a trig function here. So here's our interval, 0 to 2 pi essentially. If I can bring that back. So we're going to need critical values over that interval. X plus sine x. Okay. So we're going to take the derivative of this function, set it equal to 0. Let's try to find some critical values. So we differentiate x plus sine x. And that's the derivative of sine is cosine. Derivative of x is going to be 1. So this is 1 plus cosine x, this derivative. So we get 1 plus cosine x is 0, which means cosine is negative 1. So again, like I've mentioned in the past, this kind of curve shows up a lot. So generally just think of the sketch of cosine, at least I do. So it looks like cosine's negative 1. That happens when x is pi here. So, okay. We got a critical value. X is pi. So a critical value at pi, and that looks like, you know, it's in the interval from 0 to 2 pi. So, okay, so we do have a critical value at pi. Now, the closed interval method requires us to evaluate the function at each endpoint. So we need f of 0. We need f of pi. These are the endpoints. It's 2 pi. Right? The interval goes from 0 to 2 pi. And we're going to need the value of the function at the critical value, f of pi. We just have to remember what the function was. So let's move everything down here. And this function was x plus sine x. Okay. X plus sine x, 0 to 2 pi. Now, f of 0 becomes 0 plus sine of 0. Let's kind of give us some space here. F of 2 pi will be 2 pi plus sine 2 pi. F of pi, pi plus sine pi. Sine 0 is 0. Sine 2 pi is 0. And I believe sine pi is 0. So this is 0. 2 pi and pi. Let's highlight this here. Okay, f of pi is pi. So pi is about 3.1 somewhere over here maybe. A little bit to the left there. And so, yeah, you can see here, there's an absolute min here. That's the 0. And the absolute max, we're really talking about the y coordinate value. That's where 2 pi would be. Pi and 2 pi and 0. So, yeah, we can see on the curve where the max and min is. So this is going to be the absolute max, absolute min. So we'll just simply say, hey, the absolute min is 0, while the absolute max is 2 pi. So here's our conclusion using the closed interval method. Another trig function, but this time the interval is going to be from negative pi to pi. So this is the interval that they're looking at here. All right, just going to check a few things here. All right. So we're going to need the derivative here. This is closed interval method. Yep. Okay. We're going to find our critical values. So differentiate sine times cosine and set that equal to 0 here. All right. So you can see here we're going to have to use the product rule. So we pull out the first function, differentiate the second function, plus the second function, and then you differentiate the first function. Derivative of cosine is minus sine. The derivative of sine is cosine. So, I like starting my terms with a positive value. So now we got the following equation here. Okay. So we're going to have to solve this equation for x. Now, there's going to be a couple of ways we can do this here. We can translate the sine squared term and say, hey, sine squared, move that term over here as cosine squared, and then we're going to probably need more space. Divide both sides by cosine squared, so we'll get sine squared over cosine squared is 1, and that's really the definition of tangent squared. So tangent squared will be 1, which means tangent by the square root formula is plus or minus the square root of 1, or we're going to simply say tangent will be plus or minus 1. So there's two solutions. Tangent is positive 1. Tangent is actually negative 1. So give me a few seconds here. I'm going to be right back. I got to do a quick errand. I got to move my car. Hold on. Okay, while I'm back, my father-in-law's moving my car, so all right. Okay, we're solving a trig equation here. So, if this is a trig class, I'd go to my all students take calculus. Let's see if I have that here. Because this is not going to be too bad of a situation. But I do want to go give you guys some detail. All students take calculus. Where are you? Okay, well, we'll use this one here. There we go. Now, if you guys remember from Calculus 1, tangent is really 1. Let's move this here. If we look at this, quadrant 1 answer. Opposite over adjacent. That only happens for a 45-degree angle. So that means x is actually pi over 4. This is for tangent being positive 1 here. This is what we're looking at. And then there's two quadrants where tangent's positive. It's in quadrant 1. And it's in the opposite quadrant, quadrant 3. So typically, what we say here for tangent being positive, that means it happens when x is pi over 4 here. Let me write it above over here. And since they're opposite quadrants, 1 and 3, this solution differs by a multiple of n pi. So we'll have x plus n pi, generally speaking. Now, where is tangent negative 1? Well, it's going to be over here in quadrant 2 and quadrant 4. So we're going to have to first get the quadrant 2 solution. That's found by saying, okay, we know x will be pi minus pi over 4. So it's thought of as a reference angle. And that essentially gives us 4 pi over 4 minus pi over 4 now. And that first negative angle will be 3 pi over 4. But we have the opposite quadrant solution. So you'll have x is 3 pi over 4 plus n pi here. So this is in blue where tangent is, I should say, positive 1. And then in red, this is tangent being negative 1. So those are the two solutions. But we have to go back and remember the domain here is from negative pi to pi. So what does it mean to find critical values now from negative pi to pi here? Okay, they restricted the domain. We don't need every solution. We just need the solutions that are in this interval here. So let's kind of write that down so you guys can see that. What solutions are in that interval? Well, here, if n is 0, so if we take the positive solutions, let me get that copy. Oh, come on. I just wanted the formula. So, okay, let's write it down then. For the positive solutions for tangent, n could be any integer. So we can say n is 0. If that's the case, pi over 4 is a solution. If we let n be 1, well, we're outside of the interval from negative pi over 4 to pi over 4. So we don't want to let n be 1. We can also let n be -1. And if we do that, we get pi over 4 minus pi and I take that back. This is pi, not pi over 4. So let me rephrase this. This is not the interval. Sorry, I was looking at our solution. This is the interval, negative pi to pi. Okay, well, in that case, yes, we're going to be able to do this here. We're going to let n be 1 here. And we can generate the next solution, which will be pi over 4 plus pi. Let's just do some arithmetic. That means we get x is 5 pi over 4. That doesn't look like that's going to work out for us because this is outside the interval. So any other values, if we use n as 0, n as 1, they're not going to... n as 0 gives us a critical value solution. That's in the interval from negative pi over pi to pi. But starting at 1 and beyond, we cannot use this. We could use n as -1. And let's see what happens. See if we're in the interval. That's now minus pi. So this becomes 4 pi over 4. So we get 1 pi minus 4 pi gives us negative 3 pi over 4. So ladies and gentlemen, there's your x, negative 3 pi over 4. Okay. So far, with this tangent being one solution, we only have 2 critical values. Let's use the -1 solution for tangent, which means x is 3 pi over 4 plus n pi now. So we're going to use x equals 3 pi over 4 plus n pi. Now, when n equals 0, x is 3 pi over 4. So that's in the interval. So we're happy about that solution. If we said what's n being 1, that means x is 3 pi over 4 plus pi. Again, in order to add these, we need the same denominator. So this is going to give us x is 7 pi over 4. This is going to be outside the interval. Three pi over 4 plus n pi. Now we're going to let n be -1. We get x equals 3 pi over 4 minus pi 4 over 4. X is negative pi over 4. And that is in the interval. So if we had to list the critical values now, right? X is going to really be, we'll say plus or minus pi over 4 plus or minus 3 pi over 4. Yeah. Okay. These are all the critical values for this. So even in this picture, I'd say this is where you have the pi over 4. Over here is 3 pi over 4. We can kind of fit that in. And then over here, just all these horizontal tangents. negative pi over 4, and then over here, negative 3 pi over 4. So we're going to have to plug in for this function right in here. Sine, cosine, all of those values. So let me write down the function here. The interval is negative pi to pi. So I'm having a little trouble writing this stuff here. At this angle. So you're going to have to evaluate f of negative pi. You'll evaluate f of pi. You'll evaluate f of pi over 4. F of minus pi over 4. F of 3 pi over 4 and f of minus 3 pi over 4. So that'll be sine negative pi times sine pi. Sine pi, this is cosine pi. And it's negative pi. Okay. Sine pi over 4 cosine pi over 4. Sine negative pi over 4 cosine negative pi over 4. Sine 3 pi over 4. Let's get all of this to the side here. Cosine 3 pi over 4. Sine negative 3 pi over 4 cosine negative 3 pi over 4. So what I personally would do here, let me try to move it all over. We're going to have to find the max and min. So since some of these are negative, I'm going to use even and odd function properties. Okay? This will make my life easier, and I like my life easier. So sine is actually odd. So this would be cosine. Cosine is even. Okay, so I'm going to use these properties. Now, let's think of what sine is. Sine of pi, this is actually 0. Cosine of pi is negative 1, but this is now going to give us a negative 1 times 0, which is 0 times negative 1. The answer is just simply 0 is what I'm saying. So I'm going to start to use some of these properties here. Similarly, sine of pi, we know is 0. Cosine of pi is negative 1. So this product is also 0. Now, I can do something here. I could go back and take a look at the curve. Sine of pi and negative pi, those are the endpoints. Yeah, sure enough, you're 0 on those endpoints. I'm going to get rid of that highlight. So you are 0 at the endpoints. Okay, that's good to know. So, we're looking at the picture to verify everything. Let's do the rest. Sine of pi over 4 now is the square root of 2 over 2. That's the same here for cosine. So you get the square root of 2 over 2 times the square root of 2 over 2 will be 2 over 4, which equals 1/2. So f of pi over 4 is 1/2. We're going to use properties again for even and odd, meaning I got negative sine pi over 4 times cosine pi over 4, because sine is odd and cosine is even. So we're going to get a really negative 1/2 here if we go through and use the last piece of information and the fact that there's a negative sign. All right, now we're losing some. This is going to be tricky. Let me do this. Add a page. And let's try to move it all down if we can. And, you know, we got the F portion. Come on. Okay. Now let's remember 3 pi over 4 here. All right, so like pi over 4, 3 pi over 4 is in quadrant 2, all students. So sine is positive. Square root of 2 over 2. Cosine, though, will be negative. So positive times a negative will give you a negative. So at 3 pi over 4, we'll have a negative 1/2. Again, properties of even and odd. This will give us a negative sine of a positive 3 pi over 4, cosine of positive 3 pi over 4. So this will be here. Sine, let's think about that. Sine in quadrant 2, all students. Oh, that's positive. Square root of 2 over 2. Cosine is negative. Square root of 2 over 2. So this would be a negative times a negative gives us a nice positive. So, okay. Now, what it looks like to us, or what it looks like to at this point is the max is 1/2. The min is negative 1/2. So pi over 4 is a max. Negative pi over 4 looks like it's a min. And that actually looks pretty good, because this is what we're saying. You got a max here and you got a min. That's true. At 3 pi over 4, you should have a min. It should be negative 1/2. Yeah. At 3 pi over 4, that looks good. And you're going to have a max at negative 3 pi over 4. So, yeah, sure enough, that's exactly what we're seeing here. So our analysis does match the picture. So we're happy about that. And, all right, we got the max and min. So let's just write this down. The max is going to be positive 1/2. The absolute min will be negative 1/2. So I went through all the gory detail for this one question. Okay. And my writing's a little weird because of this angle that I'm at. I'm at a very difficult angle. All right, number 9. The interval now is from -1 to 2. You can kind of see it over here. And we got to find the critical values. So the derivative of this function, it's a linear function. 5x plus 1 is 5. So to say we're going to set this equal to 0 and solve for x, that means 5 is 0. That never happens. This means there is no critical values. So you only have to evaluate the function at the endpoints, f of -1 and f of 2. So there is no critical values. And the function is 5x plus 1. So let's write this down. So again, since the derivative is never 0, just to emphasize this point, the derivative is never 0 because the derivative is always 5. So that means there's no critical values. And you don't see any hills or valleys in that line there. So simply plug in -1. We get -5 plus 1, which equals -4. Plug in 2 now, and you get 10 plus 1, which is 11. So just evaluate the function at the endpoints by the closed interval method. And we see really here, in one case, you have a min, and the other case, you have a max. So absolute max is 11. The absolute min is -4. So, ladies and gentlemen, there you go. You are standing. The altitude over here is going to be 11. Okay, see it there. And then -4, your altitude is, you're below sea level. That's where -4 would be. So you guys can see that. +11, -4. Closed interval method. The closed interval they give you is -1 to 2. So let's get the last one. This function over the interval from -2 to 1, remember you have a sharp, it's called a cusp, by the way. Your function's not differentiable at those cusps. Let's show you what I mean by that. This is x to the 2/3. We actually seen that this was not differentiable at x is 0. Okay, we proved that. We talked about differentiability. So when you take the derivative of this x to the 2/3 power here, let's double check. Yeah. You get 2/3 x to the 2/3 minus 1. Well, that's going to be 3/3. So this will be 2/3 x to the minus 1/3, which really means we get 2/3 cube root of x. Now, if we're looking for critical values, we got to find where the function equals 0 and its derivative equals 0. Or where the derivative does not exist. And the derivative will not exist if we set that denominator equal to 0 and solve for x. And we get the cube root of x is 0. Well, that means x can only be 0. Just solving that equation. See, the cube root of any number being 0 implies the number must be 0. And so this is where the function at x is 0 is not differentiable. So we're not differentiable at x is 0. But notice you are in the domain of the function. That this location where x is 0 is on the curve. And that's an important detail. Why is this not working for me? All right, that's a very, very important detail. 0, 0, x equals 0 is in the domain of this function, and it's in the interval. So sure enough, this is a critical value now by definition. All right, so we have to find the value of the function at the endpoints by the closed interval method, the endpoints being -2 to 1 now. Here's the endpoints, and we have to find the value of the function at the critical value. Well, we already know that was 0 because we looked at the picture. You know, but I mean, if you said, how would I really do this? Well, remember, this is x to the 2/3. So you would plug in the 0. You got to evaluate 0 to the 2/3, which gives you 0. You have to do that for the endpoints as well. You have to find f of -2, which will be -2 to the 2/3. And you have to find what f of 1 is, which would be 1 to the 2/3. Well, that one's easy. That's 1. So far, we've done the easy ones. We just have to evaluate the f of -2 here. And we'll do that down here. So, all right, let's find out what this is here. So I'm going to go do a deeper dive. This is going to be -2 to the 2nd power, and then we're going to take that to the 1/3 power. So this gives you really 4 to the 1/3 power, or this would be the cube root of 4. Okay. The cube root of 4. So I'll write that down here. Well, let's leave it. Let's look at what this is here. Okay. Cube root of 4. We're going to wake up our TI calculator and find what the cube root of 4 is. If we know that numerical value, compare it with 0 and 1, we can find which one's the largest, which one's the smallest, and we could be done with this. So in our calculator now, the cube root of 4, we take 4 raised to the 1 divided by 3 power. That's the cube root. And this is about 1 point. We'll go to the nearest, I guess we could just go to the nearest tenths, really. It's about 1.6. All right. So it's about 1.6 approximately. Okay, so we have the value of the function at the endpoints, the value of the function at its critical value being 0. So we know one thing here, 1.6 is, this is the absolute max, and 0 is the absolute min. So we have the absolute max of 1.6 at -2. And yes, we can kind of see that at this picture. This is the absolute max location, and then you got the absolute min location at 0, 0. Those are the coordinates. So it does look like it makes a lot of sense, but we just have to formalize the answer. And absolute max, we can just say this. So we can keep the symbolic form. Oh, my pencil keeps coming off. It is the cube root of 4. The absolute min is 0. So ladies and gentlemen, I'll send you guys this again. Extra examples. Hope you enjoy the presentation.